In this section, we're going to look at a procedure which allows us to compare several population means using a procedure known as ANOVA, or the analysis of variance. The procedure was actually initially suggested by Sir Ronald Fisher in the early 1900s. And of course, there were other statisticians in Europe, particularly in Germany at the time, that were working on the procedure as well. The idea is pretty simple, at least now is simple, because we know what these statisticians had in mind about almost 100 years ago. But the idea of Fisher was to partition the total variability in, let's say, y values, which we call the response variable or dependent variable, into sources of variabilities that make up that variation or variability in dependent variable. So what ANOVA is actually a procedure that provides us with means of comparing, again, two or more population mean mu's. The case where we actually have two population means, we've done that. We've done for independent samples, that is, we've done that just before this section, in fact, where we look at two sample t-tests with independent samples. So we can also do those t-tests for independent samples for two populations using analysis of variance. But the reason we don't is because the procedure is easier to do, particularly if some people have to do this by hand, using the way we did it in previous section. But the ANOVA is also definitely doable for a situation like that. So here I have the objective. Again, is we want to compare several population means on a variable that results from classification by one other variable. Now this other variable, we call it a factor. Okay, this variable is actually an independent variable. We'll get to the list of variables in a moment, but that's what this one is. It's different from the variable up here, where is the response variable. Okay, so this would be independent variable, which we call a factor. Now, possible values of the factor are called levels of the factor. Okay, levels of the factor. So just the terminology. Now, ANOVA is indeed an experimental design where we actually do what we call a completely randomized design framework. It is experimental design because it has the three pillars of an experimental design. That is, there is replication, randomization, and often there's a control also. So this is an experimental design. Okay, now the simplest form of ANOVA, by the way, is the one that we're looking at. It's called a one-factor or one-way ANOVA. And again, within the context of design, statistical design, that is, this is known as a CRD, or a completely randomized design. So what is a completely randomized design? Very simple. In the case of a completely randomized design, subjects or objects, items, or whatever we have, are assigned randomly to treatments. Now the word treatment here, remember, treatment is a variable. The reason it's called a treatment is because Sir Ronald Fisher was actually an agronomist, and he worked in the field of agriculture. So a lot of times they literally apply these treatments, would be like, for example, pesticides, to plots of lands, and then they try to look at the yield of the crops. So that's the origin of the word treatment, which still stays with us. As you will see later on, treatments are not necessarily pesticides, potash, nitrogen, or things like that. They could be other things. Okay, and there's only one treatment here. We have only one treatment with two or more levels. So for example, again, treatment could be pesticide, and I could have pesticides A, B, C, D, E, whatever, however many levels there may be. Okay, and here's a summary of the variable types that we often talk about in an ANOVA. We have our dependent variable. Of course, this is the response variable, or the outcome variable they call it also, and it's response to different levels of independent variables, and it's the actual measurement that's collected under the conditions of the design. So for example, if I'm measuring the pressure of tires, then that's what dependent variable is. Or if I'm comparing again the yields of two different mutual funds, the yield in this case would be dependent variable. The two types of mutual funds would actually be levels of the factor mutual fund. Mutual fund A, mutual fund B, those are the levels of that factor. Independent variables, we actually have two kinds of independent variables. One is the classification variable, and the other one is called treatment variable. So we got these two types of independent variables. So first, the classification variable. These classification variables are typically qualitative or categorical in nature. That's why they're called classification variables. And what's important about them is that the experimenter has no control over these. So for example, if I talk about regions in the United States, and suppose for now we'll make it simple, we have north, south, east, west regions. So see, I have no control over the regions. Or if I look at the 50 states, we have 50 states, it is what it is. So I cannot manipulate number of states, all of a sudden grow them to 75. So that would be the classification variable. And then there is treatment variable. This treatment variable is actually modified, or there is a control variable there. So the key is that treatment variable is often modified or controlled by the experimenter. Okay. And a treatment variable is also called or known as a factor. Okay. So here I have a couple of examples. Hopefully it will clarify these definitions or terminologies for us. So first example, we're looking at dependent variable. That's actually what I'm collecting, let's say, for these different regions. So my dependent variable, my response variable, if you will, sales, I'm looking at sales by regions. So region is going to become our factor or treatment. So notice this is not a pesticide. I have a region as a treatment. And these are the levels of that factor. Region. North, south, west, east. There are 4 levels of that. My next example I made up was tire wear. So that's again my response variable. My treatment in this case or factor would be brand. Suppose I have 3 brands of tires. Okay. And I mean, the brand here would be low, medium, high, not necessarily like BF Goodrich, Michelin, like that. We're talking about the brand, and these are the levels of the brand. So we're going to look at the tire wear by, in other words, by whether the tire is low grade, medium, or high grade tire. For a given brand, this is going to be, let's say again, Dunlop, or it could be anything. Here's another example. Relates to business and finance. Let's say a finance researcher conducts a study to determine whether there is a significant difference in application fees for home loans in 5 geographic regions in the US. She examines 3 different types of lending organizations. So, what are, let's say, independent variables in this case? There you have it. Our independent variable here is, or R I should say, geographic region, which is classification, right? And type of lending organization, that would be our factors, right? Those are again the types of lending organizations. And remember, these lending organizations, 3 different types of lending organizations. And what are we collecting in each of these lending organizations, we're collecting information about application fees. So the dependent variable, the outcome variable, the response variable is application fees. Okay. So again, here's our classification variable region. Notice we have no control over the region. We cannot manipulate that part. And the type of lending organization, those we have control over. So I can choose, let's say, 3 randomly selected lending organizations, or I can pick small versus large organizations, however the researcher wants to. So what is the null hypothesis? That's all we want to do with the ANOVA in this section. The null hypothesis says, however many populations we are comparing, so in this case, it looks like I have 1, 2, 3, all the way up to k populations. K could be 10, 20, 4, 10, again, 7, 6, 12, whatever, however many populations we want to compare. So the null says that there is no difference between those means. They're all the same. Okay. Now the alternative is what we're really interested in. The alternative here says not all means are equal. Some actually symbolically write that as mu I not equal to mu j for I different than j. That means at least one pair of means are different. Okay, so for example, mu1, mu2 could be different, but mu2, mu3, mu4, assuming I have 4 populations, those could be equal. So that's the significance of not all means are equal. Now, here I'm going to try to explain the logic of ANOVA, how they went about putting this table together, analysis of variance table together. So first of all, here I have made up 2 sets of sample data. So here I have 1, 2, 3, 4, 7, 5. The number doesn't matter. But looks like I have 8 dots. This is the dot plot. So, but what's important is that if you see, there is a spread between these data points. So the spread is rather large. And then I have a second sample, and the spread within these scores is rather large also. So I have here variations within each sample are nearly the same, right? Inside, they are almost the same, the spread, but they're rather large. So in this case, X bar 1, X bar 2, they look clearly different, right? They're not the same. So the question may come up is this. Is the sample mean, or are the sample means different because the mean of the populations are different? Or is there another reason why those 2 sample means are different? Namely, because the deviation within 2 samples are large. Again, look at the deviation here. Large, so that's what's causing these X bars to shift. But in the population, if these were closer together, perhaps the deviations, maybe X bar 1, X bar 2 would have been much closer together. So this becomes the basis, the mathematical basis for the work we're going to do. Now, here I have another example. Now, in this example, look at this one. Remember how dispersed this data was and how dispersed the second sample was. Both of these were independent random samples for random variable x. This is our dependent variable. X is our dependent variable. Now, in the second drawing, what I've done is actually I created same data points, only I made the deviation. See how they bunch around X bar? And the second sample, the observations bunch about X bar 2. So I reduced the variability within each sample by doing that. Okay, so I can no longer now attribute a difference, significant statistical difference between X bar 1 and X bar 2 due to those large within deviations. Now I can say, well, look, deviations are under control, very small. So there is a discrepancy because this distribution comes from a different population than this distribution does. So therefore, X bar 1 is different from X bar 2 in this case because the population means indeed are different. It's not due to the variations within the populations. Okay, and there you have it. So this becomes, again, the logic of the ANOVA. Now I'm going to make that and formalize this for you. So here's the actual logic behind the work we're about to see. It goes like this. If variations between sample means is large, between means the distance from here to here, okay, between these two. So imagine if I move this bunch of data points below it, directly below it, that the between variability means between the first group and between the second group. That's what the between is. Okay. If that is large, well, if that is large, that means the separation between x bar 1, x bar 2 is going to be bigger and bigger. Well, clearly, as these two distributions become separated, the distance between them increases. That's more of the evidence that the population means are different, right? So, if variations between the sample means is large relative to variations within the samples, remember within means inside and inside here, then we can imply that the two population means are different indeed. Now, for simplicity, otherwise this would be very cumbersome. For simplicity, we assume that within variability here and within here are exactly equal. Okay, that's a simplifying assumption. So we're going to assume that for each sample, the within variation are the same. And of course, in the population, it's going to be unknown. And if they're the same in the sample, so are they in the populations. And what's important is that they are equal. Okay, and this assumption has fancy names that go with it. It's called homogeneity of variances. And some call it homoscedasticity, especially in regression. They refer to those as homoscedasticity. Okay. Now, how do we test the assumption that the variations are equal? We can actually do what's called a Levine's test for equality of variances if you wanted to. I just throw that out there, and Minitab does that test for equality of variances within two samples. We can actually formally do a hypothesis test of that. Now, one thing, by the way, I want to mention is Levine's test. In statistics, don't be surprised if a lot of the procedures seem to have the name of people attached to it. Okay, and in fact, in this video later on, you're going to see that. We're going to hear some names. The reason is because statistics is a relatively new field in mathematics. Formally, it's about only 300 years old as a science, that is. The use of statistics goes back to the time of Romans, right? So, I mean, anybody that collects information, data, even simple, how many bills of whatever wheat there are. So that would be some kind of descriptive statistics, right? But formally as a science, it's relatively about 300 years old. So a lot of the procedures are up and coming, or they have been, it hasn't been there. People have actually created these. So I already mentioned the name Ronald Fisher. Okay, so here is another name. Levine is the name of the statistician who proposed the procedure. Okay. Now, here I'm trying to again reinforce the idea of variability within and what is variability between here. Remember, within means inside to within. So the variability of these dots inside themselves, that's what the within variability is. The variability here and the variability here. We assume that these variabilities are equal but unknown. Now, what do we mean by between variability? We're talking about between the population variabilities. Now, look again. As this between variability, between these, and I made up three populations here. As the distance between the mu's increases, that means the variability between is also going to increase, right? So the larger this between variability between these population, again, the more distant they become from one another. And the more separation, the more evidence that the means are different. Okay, so we're going to make it the rule for our ANOVA test, in fact. So let's agree that if the variation between the sample means is large relative to the variation within the samples, then we're going to conclude the means of the populations are not all equal. That means these means are going to be farther and farther apart. The larger this ratio, that means the more the numerator here is, see this variation, which is relative. We're going to look at between. We're going to form a ratio of between variability to inside variability. Inside, remember, they're all the same. And the bigger that ratio, the farther apart the means are. So pretty clever, huh? Now, you're about to see some arcane, strange-looking mathematical expression. I thought it's good for you to see it, even if you don't follow what you're about to see, folks. Do not worry about this, okay? Because we're going to do everything in Minitab, right? So I'm just going to flash this so you kind of at least see visually that there is some kind of a mathematical logic. It has to be, right? Everything we do has to be governed by mathematics because we're in a quantitative field. So I'm just going to flash this strange looking formula in a moment, but this is the basis, the thought process behind the formula you're about to see here. Okay, so remember, the analysis of variance is a partition of total variation in dependent variable, the y variable, if you will. So what we do, in fact, we say, okay, well, let's look at that total variability, and that's going to be equal to, I'm going to partition it between the variability that's between the samples and the variability within each samples. So this total variability, for example, here we're talking about, by the way, is the variability for all of these points combined. That's all of them combined, regardless of where they have come from. That's what we mean by total variability. So let's say I have, I don't know, let's say my population here, I have 100 points here, 200 points here, 200 points here. So my population size combined is 500. This would be the total variability of those 500 scores, regardless of where they have come from. Okay, so that's what this is. Now, and then this next statement, so when we talk variability, let's agree by variability, that translates for us into sum of squares. More specifically, it's the sum of the squares from the mean. Okay, and the reason it's the squares, because if we don't square it, we just sum deviations from the mean, we're gonna get 0 every time. So the reason for squaring here. So having defined what we mean by total variability, and also here defining variability as sum of squares, check this out. We can write the total sum of squares, therefore, as sum of squares between groups plus sum of squares within group. Remember, so total variability translates to total sum of squares, and variability between translates into sum of squares between. Variability within translates into sum of squares within each group. And this is just a notation. This is not the formula I was telling you about. That's kind of convoluted. You'll see that in a moment. So SST, total sum of squares, equal SSB plus SSW. Okay, and that becomes the foundation for what you're about to see here. Again, I'm forewarning you here. Don't worry, folks, about this. It's like, you know, how am I going to do this? You're not going to. I just want to show you. There you go. That's what that formula is. So this is what we mean by overall sum of squares, which isn't difficult. That looks like individual deviation from the mean, squares it, adds them up. That's pretty easy. It's this one. That's kind of cryptic. Okay, and that measures the sum squared within groups. This is how you calculate sum of squares. Notice these are sigma means sum, sum, sum. Okay. And here I'm assuming that how many groups there are j groups, and there are going to be k observations within j groups, each of those j groups. Okay, so anyway, that's what that is. That's the mathematics behind it. So if we were to do ANOVA by hand, folks, we had to do this. But thank God we're going to do this using Minitab. So, and this is kind of a final word about analysis of variance, and then we're actually going to go through and actually see an example. So, just to recap, we're going to take the ratio of average variations between groups and average variation within. Remember, that's going to be a relative size of those ratio. This is going to be in the numerator between. This is going to be in the denominator on this ratio. Remember, ratios are fractions. And we're going to assume equal but unknown deviations. Now, the ratio is what we call an F ratio. And again, it goes back to the mathematics of all of that stuff that we're not covering in this course. But that ratio actually that we're talking about in the first bullet forms a probability distribution that is known as Fisher's distribution here. F stands for Fisher distribution. And that's going to be our test statistic. And if F, that ratio is large, remember, if that ratio is large, that means the numerator is getting bigger, means more and more separation between these populations. Okay. And so if F is large, we reject the null, and the question is, how large is large? Well, that translates into a p-value for us. Okay, that's how we judge how large is large. And just a note here that for all your ANOVAs, they're all going to be right tail. We don't have two tail ANOVAs or left tail ANOVAs. Okay, because we want to reject the null if F is large. We want clear separation between the means. So for that reason, all ANOVAs are right tail. Now, what are the assumptions for this? Not too bad. First foremost, we have that simple random sample assumptions. So we're going to assume, let's say I have samples coming from 4 regions, north, east, south, west. Every one of those is going to be a simple random sample. Those samples have to be independent, right? They're not like paired samples or dependent samples. That means what happens in one region has no effect on what happened in the other region. And for each population, the dependent variable has to be normally distributed. Your y values have to be normally distributed. And the standard deviation of the variable under consideration are unknown but assumed equal in every one of those, the levels of the factor or the levels of the treatment. So we're assuming equality of deviations. Now, the simple random sample, we can ensure that by the way we conduct the experiment. Independence is by the manner in which we conduct the experiment. And number 3, these must be normally distributed. We can always do a box plot. We can do a histogram. We can do a probability plot. Remember, we did that in the previous lecture. A PP plot or a QQ plot, they call them, probability plots. And finally, for this one, is how do I check the standard deviations are equal? There you go. You can consider the easy way out of this, folks, is this. You take the ratio. Let's say I have 5 populations. I'm comparing the means of 5 populations. So when I take a sample, I'm going to have 5 sample means, right? And I'm going to have 5 sample variances. And of course, from that variance, I can calculate standard deviation, right? By taking the square root of it. So if I take the ratio of the largest sample standard deviation to smallest sample standard deviation, and that's going to be less than 2, the magical number is 2. If that's less than 2, you're going to say, okay, that's met. And this rule of thumb is known as Rule 2 for the ANOVA. Or you can actually do a more fancy work, which I'll do for you later in Minitab. You can do a probability plot of the residuals. What's a residual? A residual means leftover. Residual is the difference between an observation and the mean of the sample. What's left over is called residual, or the error. Okay, so that's how you can check that assumption. And there you have it. Now, well, here we have an example. We actually will go to Minitab and actually do this in a moment. Okay, now for this exercise, we have a milk company has 4 machines that fill gallon jugs with milk. The quality control manager is interested in determining whether the average fill for these machines is the same. Okay. Now these could be machines from the same brand, okay, whoever makes these machines, or they could be machines from 4 different manufacturers. We don't, just for this part, we don't care. It's just we have 4 machines, we want to compare them. The following data represent simple random samples, assumption 1, of fill measures in quarts for 19 jugs of milk. Okay, now remember 4 quarts, I believe, 4 quarts to a gallon. So these numbers should be mostly about 4, each of them, for each of these jugs of milk, filled by 4 different machines. Question, is there a difference in mean filled jugs between the 4 machines? We're talking about population means. That means if all of these milk jugs that are produced, thousands and thousands and thousands from machine 1 versus thousands machine 2 and so on. So notice, by the way, here again, we got to be really wary of small samples. It's very, very risque to make generalization based on just 4 scores here, 4 here, and so on. However, in this case, because anything that's done by the machine, it's an automated process. So it's got to be fairly stable, although still it doesn't get around the fact that the samples are small. But I'm just trying to make a positive case out of small samples here, I suppose. The fact that the machines do these are fairly reliable, and they do them the same way. It's not like humans actually filling up these jugs. So having said that, you can kind of see the numbers for machine 1 are on or about 4. It looks like in all cases they overfill ever slightly. I mean, what's 4.01 quarts as opposed to 4 quarts? Not much. This one, machine 2, the same, right on 4, 4, 401, 402. A couple of them small, but again, but not by much. So visually speaking, by the way, I would say, look, these are all about 4, 4, 4. But actually, take a look at machine 3 here. See, machine 3, it's not much again, not much, but still, notably, I don't see 4, 4, 4, 4, like you see here. So there may be something going on there. And that's why we want to run Minitab and just look at this objectively. And I did, and here's actually what turned out to be, interestingly, from Minitab. I'll go to Minitab and show you how this is done in a few minutes. It's very simple. But we really, folks, we don't want to do this by hand, so you're not even seeing the formulas here. So please make sure you use Minitab for this. Unless you're adamant about doing it by hand, then you have to find those formulas in our textbook by Diaz. Okay, so from Minitab, look at, this is the F ratio that we got. This is the ratio of variability that's between machine 1, machine 2, machine 3, machine 4, divided by inside variability. inside, inside, inside. And we assume all of those inside within variabilities are the same. And we'll see in the ANOVA table exactly what that common deviation is going to be between the 4 machines. But how do I know if 10 is large? That's what I was saying. Look at p-value right next to it. P-value 0.001. Remember, small p-values, we love them, because that means for this example, we have clear, convincing evidence, far beyond reasonable doubt, clear, convincing evidence against the null. So we're going to convincingly reject that null hypothesis. Probability I made the mistake saying that is 1 in 1,000 according to the p-value. Okay. And of course our decision, and notice by the way here, I didn't even give an alpha. With p-value, you let the data speak for itself. So alpha 05, alpha 10%. What alpha do I use? Whatever you want to use. I'm not using any alpha. I'm just going to say, wow, p-value, I know the strength of the evidence. P-value less than 0.1 means very, very strong. Closer to 0 means the stronger, stronger, stronger. That's all I know. So I feel pretty good about this rejection. And my decision is that we're going to reject the null hypothesis, conclude that there is a difference in the average fill rates between the 4 machines. Period. Done. Now, next to that, I actually have raised a question now. Okay, well, we're saying, I'm saying, you're saying, we're saying, there is a difference in the fill rate in the machines, 1, 2, 3, 4. Well, can we compare and see which one or ones are different? Maybe mu1, mu4, machine 1, machine 4. Look at machine 1, machine 4. They look about the same. So I'm sure there's no difference between them. Maybe 1 and 2 are about the same. 2 and 3 may be the same. But 1 and 3 look different. You see how I'm looking at pairwise, 2 at a time comparisons. So that's what we want to do. Next, we want to tap into that. So which pairs are significantly different? And with that question, I haven't forgotten. I owe you a Minitab run on this, right? We'll do this in a few moments, but let's take a look at the continuation, because otherwise we will not understand the output from the Minitab. So let's continue on. So how am I going to compare these means? Okay, so the comparison procedures that we're going to look at assume equal variances. Remember, that was the very assumption. There was assumption number 4 right in here, right? Unknown but equal. So it makes sense our comparison procedures make that assumption. And here I have the list for you. These are the things that Minitab actually does. It does the multiple range test, and there is a description of what it's doing here. With multiple range test, 2 key. This is also known as 2 key HSD, which means or stands for an acronym for honestly significance difference. That's what he called it. Well, this Tukey gentleman, by the way, Professor John Tukey, he passed away in July of 2000. So it's almost next month, next July, it would be 20,000 he passed. He passed at the age of 85. He was initially actually a chemist. He's got his, I believe, bachelor's and master's from Brown University, and then later on moved to Princeton to get his PhD in mathematics. A brilliant, brilliant gentleman. He did a lot of work in exploratory data analysis, but then he was also into a lot of stuff. In fact, he coined the term digit, bit, all of those. And he was a member of IEEE, International Engineering Society of Engineers. So he was actually a member of those. He actually is a gentleman that devised the fast Fourier transform that is used even today in military and in most of engineering applications. He's believed to have contributed to, during World War II, to design of U-2 spy planes. So anyway, if you want to go to Wikipedia and search for this gentleman, John Tukey, you'll see and hear a lot of very impressive resume of this gentleman. And he actually came up with this, as you can see here, 1953. I found these for you if you're interested. Now, something I want to note here for you, by the way, Minitab does Tukey HSD. One of the assumption for this multiple comparison procedure, Tukey HSD, is that the samples must be equal. Okay, so if I have 4 samples, each must be size 10. Looking at my data up here, they're not equal samples, right? 4, 6, 5, 4. They're different sample sizes. So the Tukey HSD would not be appropriate for this. However, there is a modification to that, which is Tukey-Kramer. Tukey-Kramer, and that's right in here. That is truly a modification. This gentleman, Kramer, he actually, Clyde Kramer, 1956 is when he actually modified the procedure by Tukey, and he made it to where it works for all samples, the different sample types. They don't have to be equal. Now, Minitab, by the way, internally is programmed to do that. So we don't need to go and say, oh, do a Tukey-Kramer for me, or can you do a Tukey HSD for me? It's just going to be Tukey. Okay. But again, these are the actual citation, and look at the dates. This is in Biometrica. Okay. The other multiple comparison procedure here is Fisher, discovered again or proposed by Sir Ronald Fisher. And for the Fisher, it's not popular compared to Tukey's, okay? Because with Tukey, actually, and I tell you more about this below here as we go through, but one thing that Tukey, the strength of Tukey procedure, multiple comparison, is that it controls the what we call the family-wise significance level of alpha, or simultaneous confidence intervals here, or confidence levels, sorry. I'll tell you more about it, but that's the strength of Tukey's procedure, which Fisher's lacks. Then the other multiple comparison method in Minitab is Dunnett, named or discovered by Canadian statistician Charles Dunnett. And with Dunnett, though, you compare the treatment groups to, you have to have a control group. The example I have up here, there is no control group, so we cannot use that. Okay, so we cannot run Dunnett on that. But if you had it, you can use this one. And they all accomplish the same. The objective of all of these is the same. Which means are the same and which means are different. And this is the resource for this test, new tables for multiple comparison with a, oops, sorry, I missed the C here. That should be with a control. There you go. Okay, now it's well. All right. And let's see. The next one is SU-MCB. Okay, and multiple MCB stands for multiple comparison best. And this here is this identify the groups that are the best. So with this one, what you do is you choose, and it's right in here. Largest mean is the best, or smallest mean is the best. Which one you want it to be the best case, the best mean. And then you compare each of those to that one. In a way, it's kind of like a control, but you decide on those. And this is again the citation to actual, where you can find the procedure. If you want to read more about it or find out more about it, this is actually a book you can purchase. And this is the link. This gentleman, Professor Su, Jason Su, was actually a member of Ohio State faculty at the statistics department. Okay, now we're almost getting to the end of this, to where we can go to Minitab. So now we're going to look at multiple comparisons here. And this is what I want to point out, the strength of Tukey versus Fisher's. So when we actually look at, when we conduct these pairwise analysis of differences, okay? In other words, one thing we could do to begin with, let's say I have 4 groups. I can compare subgroups, right, factors. Suppose I have 4 machines, right? I can do a paired, not a paired, but just a 2-sample t-test, right? I can do machine 1, machine 2, machine 1, machine 3, machine 1, machine 4, machine 2, 3, 2, 4, machine 3, 4. So there are four independent t-tests I can do. Well, if we do those pairwise analysis of differences, is what I have here. That will result in what we call a buildup of a type 1 error. Okay. Well, one way to get around it is to go through the multiple comparisons these gentlemen have proposed. So multiple comparison method kind of nips that in the butt, and it just takes care of that part. To where our overall type 1 error of all of those comparisons is going to be 0.5, for example. That's very important. Now, some of these, by these we're talking about multiple comparison methods, and there's more of them, by the way. It's more than what we have up here. These are not the only ones. There's a dozen or so of these multiple comparisons. And some of these multiple comparison methods control the overall type 1 error, such as 2 keys, and others for type 2 error, which none of them are listed on that list, and some require equal sample size, again, like the 2-key HSD. Okay, so we just got to be careful which one do I use. And then here is another important idea about these pairwise comparisons. We have 2 kinds of comparisons, pairwise comparisons we do. One is posteriori versus a priori. Okay, so what's the difference between them? Well, in a posteriori comparison, these comparisons you make pretty much after you reject the null hypothesis in the ANOVA. Okay, so it's after fact, after the experiment is concluded. You decide to test these significant differences, just like the ones we are about to do with the machines. This would be posteriori. The ones we do in this course are all posteriori. The ones you do if you ever do this, for your research, for your work, whatever reason, most likely you do posteriori. The a priori here, comparisons are made when you determine, the researcher determines actually before the experiment. Like you say, well, I want to check out machine 1 versus machine 4. That's really what I want to do. So let's do this experiment. You see that? You already know ahead of time what you want to do. So just 2 different ways of comparing. And of course, for these 2, the error rates and techniques are different for the 2 types of comparisons. And again, the posteriori is also called post hoc comparison methods. Okay, now remember the terms here. I have post hoc because I believe in your final exam there will be questions. Remember, your final exam is made up by the main campus. Okay, and part of that is for assessment. There's going to be 2 pieces of it. In that assessment part, don't be surprised if they mention, or there will be a question about something with post hoc in it. Okay, so now you know what post hoc means. These are posteriori. That means post hoc comparisons are done after you reject the null hypothesis in an analysis of variance. If you don't reject, by the way, if you don't reject the null hypothesis, you see all these means are the same, then we never do a multiple comparison. It doesn't make sense. Because when we don't reject the null, that's when p-value is large. When we don't reject the null, we're saying there's no difference between them means. Well, if there's no difference between them, why do I want to compare them? They're the same, aren't they? So you only do post hoc after we reject the null hypothesis. Remember that one. And I have finally for you here, and this is what I was talking about, and after this we go to Minitab. So with ANOVA, again, it's like, well, why don't I do independent t-test to begin with? Compare these 4 machines. There's 6 combination of them, by the way. When you pair them, when you have 4 objects, there are 4 choose 2 ways in combinatorics language. 4 choose 2 ways of selecting these comparisons. Again, machine 1, 2, 1, 3, 1, 4. 2, 3, 2, 4, 3, 4. There you go. I like that. So, assuming I have 4 factors, right? There are 4 levels of the treatment variable. Then there can be 6 different pairwise. Pairwise means 2 at a time. Tests with 4 groups. Now, let's say I want to do each of those, do independent samples t-tests for each of those at alpha 05. So here, this is going to be capital. The probability of committing at least a type 1 error by conducting 6 different pairwise tests is going to be this one. Probability of at least 1 is 1 minus probability of 0 type 1 error, no type 1. So I'm using the law of complements here. At least 1 means 1 or more, right? Well, the whole thing, whether you make no mistake or many mistakes, the sample space is 1. So that's why there's 1 here. It's going to be 1 minus no type 1 error. Well, when I do 6 pairwise experiments, each at alpha 05, probability of a type 1 error is 05. That means no type 1 error would be 0.95, right? There are complementary events. And because these are independent tests we conduct, so by law of independence, we have 0.95, 0.95, 95, 95 times each other. It should be 6 of them. And if I did the math right, there you go. Look at that. 26.5%. Whoa. And there you go. Let me jazz that up for you. There is 26.5%. So it really doesn't look like 05 anymore, huh? The effective error is actually far more than that. It's more than 5 times probability that you're going to declare something significant. So that I'm just going to show you, that is why we do ANOVA. ANOVA controls the overall alpha. When we say alpha 05 in the ANOVA, all of those overall is controlled for to be 05. And that's what I have here. If an ANOVA is performed on all groups simultaneously using alpha 05, the value of alpha is maintained in that experiment. Maintain means it's going to be 05. So it is, you're getting what you think you're getting. That's what that means. So, pretty interesting, folks. These analysis of variance, ANOVAs, you're getting into some very interesting ideas in statistics. Very powerful stuff. You can do a lot of stuff with this. And so we are done with this. I know I owe you Minitab run, correct? So let me go here. This is the data, right? So I've already invoked Minitab. So this data, I've typed it up in Minitab. Remember, you can do this in Excel, import it into Minitab, or just directly type those into Minitab if you like. So I'm going to pause this video, go to Minitab now, invoke it, bring it up in there, and I'll be back. Next time you see a screen, it's going to be in Minitab, okay? So we'll go to Minitab with this. Okay, so as promised, we are now in Minitab. So hopefully you have Minitab invoked. Feel free to pause the video, by the way, and kind of run your Minitab if you can alongside of it. I know it'll be difficult to switch between screens on the same units, but if you have maybe a desktop, a laptop, or a tablet, maybe it'll be easier to watch the video and run this on another device. But anyhow, however you choose to do it, feel free to pause it as we go and kind of soak the stuff up a little easier. So here's the data. You got machine 1, machine 2, machine 3, and remember, if I drag this up, there we go. These are the information, what we call the raw data. So those are the raw data. Again, our dependent variable here is the fill, the amount of how many quarts are in each milk jug. Okay, we have the milk jugs are whatever they are. And then we have treatment. Our treatments are machines here, by the way. You see that? So it's not necessarily a pesticide. It's not a medicine. Treatments here are machines. And that treatment has 4 factors, 4 levels. Okay? So look how simple it is, folks. I'm going to go to, in order to do ANOVA, you're going to go to Stat. And then don't go to basic. Remember basic? We've been in basic for the last 3 workshops. So continue on that journey. You go to ANOVA. And without going over, you see how you have all these different kinds of ANOVA stuff. Again, like I said, ANOVAs and the in general linear models, these are very powerful, sophisticated methods of data analysis. So we're going to just take a look at one way, and there you go. They determine whether the means of 2 or more groups differ. Click on one way, and let me erase that, and let me just for now do that. Okay. In this drop down, these are your choices. Or response data. Notice response means dependent variable. Response data are in separate columns. That's exactly what we have, right? For each factor level. You see how they speak it exactly like we've made up our notes. Okay, and that's exactly what we have. Now, these are the 4 columns that are available here. When you left click once inside responses, it activates these. And all you want to do is you can click once, left click once, select. Or you can just make it go faster. Double click on each of them. Double click, double click. There you go. If you want, you can run ANOVA on just 3 of them. I'll leave the 4th one out. Maybe that was a bad machine or whatever. But we want to compare all 4 of them, right? Now, some of these fields going to be filled already again. Hopefully it's not, but let me check this out. Okay, first, what are this stuff here? The storage here. If you want, you can store fits, residuals. We don't want to do that. Cancel. The results. Just keep everything checked here. Okay, and keep it. And the display of results in, you can do expanded tables or simple tables. I'm just going to keep everything default here, okay? If you need help with any of these, by the way, look, click on help and it actually takes you outside. Maybe I shouldn't have done that, but that's okay. So there you go. So it goes into that help. This is actually Minitab help. Okay, on any of the procedures, if you hit the help button, that's what's going to happen. It takes you to the actual Minitab site and it helps you with that procedure. There you go. Methods, this is what it will do. Factor information displays this. Analysis of variance, ANOVA displays the ANOVA table. Model summary displays statistics that evaluate the model fits, including R squared. Now, usually for ANOVA, by the way, we don't need that. So I'm going to uncheck that actually, the model summary. But means, that's good. Displays the factor level means and standard deviations and confidence intervals. We'll keep that one, but I'm going to take this model summary out. We'll keep that check when we do regression analysis and multiple regression. Okay, so let me X out of this. And there you go. We're back in here. Now, so I'm going to change the model summary, uncheck it. Otherwise, I'm going to get R squares and stuff. We never talk about it. Not yet anyway. Hey, click OK. Now, on the graphs, there you go. You get a bunch of options for your ANOVA graphs. You can do, and I like to keep the box plots. These graphs, I'm interested in checking the normality. Okay, but then I can also do see the residual plot. If you check that normal probability plot of residuals, that's how I mentioned we can check the assumption of normality. Or actually no. Normal probability plot of residuals. That one, we actually check the assumption of equal deviations that way. Okay. Hit OK. And options. Right in here, you see that? We want to check these. Make sure you check assume equal variances. Otherwise, all your multiple comparisons, you got to be careful with that. We're going to assume equal variances. Also, our whole premise, the whole mathematical engine behind what we did was based on this assumption. So I'm going to check it. Confidence level. Now, because we want to do alpha 05, let's say, remember probability of type 1 error 05, so we're going to keep confidence level 95. And of course it says this is for table of means and interval plots, so we're going to keep that at 95. Type of confidence intervals, make sure that's two-sided, not upper lower. Those are one-sided. Keep them at two-sided. If you need help with that, you click on help. I'm not going to. Hit OK. There. Now, comparisons. You see that? Click on comparisons. And these are the lists of what's available. The error rate for comparisons, this is a number between like 0, 0, 1, and 50. Keep that default at 5. Okay? The error rate for comparisons. Just don't change that. Make it 5. Okay. And okay, so these are the comparisons we want to have. I don't want to do Fisher. You can notice, you can check all of it. Minitab doesn't care. It will just crank the numbers for you. But it wouldn't make sense if we got those outputs other than confusing us. We do want to keep 2-key. Remember, if the sample sizes are equal, 2-key HSD will be done. And if they're not equal, which is the case we're working with right now, it will automatically do a 2-key Kramer comparison. That's Fisher. And remember, with Dunnett, we always compare these other machines to a control group. You can actually say, my control group is machine 4. Let's say I'm examining 3 new machines versus the existing machine. So my control would be machine 4, machine 1, whatever. You can make the case for it. I'm going to uncheck that. And this is Sue, again, multiple comparison best, if you click on that. So remember, your best is largest or smallest mean is your best. Don't worry about any of these, folks. Just do 2-key. And the results, we want interval plots for difference of means or grouping information. We'll keep both of those. Don't worry about tests. Okay, and we're good to go. Let's hit OK. It's going to take a few seconds because there's a lot of information in this, huh? And boom. Wow. Guess I have a fast processor. And let me just kind of run through this real quick just to see. And then let me minimize this as much as I can so I have more of the viewing for the output. Okay. Look at all that you get for your money. Bunch of stuff. Imagine if you were to do this by hand, folks, this would take hours and it wouldn't look nearly as good. And we don't want to do that anyway. So now let me run through this output. I take a picture of this or copy it, right, and insert it inside my notebook, but I'm not going for this one because you're looking at it here. It wouldn't matter and it wouldn't make sense to do that because it's already here. So let's run through this output. So we're doing it Way Anova machines 1, 2, 3, 4. The method here. The null hypothesis, all means are equal. You see that? The alternative hypothesis, not all means are equal. Our significance level is 05. There you go. That's our default. That's what we had. 05. And there is the check we put in that box that equal variances are assumed. Now, let's go to our factor information. Remember our factor? Here is our treatment, right? There are 4 levels of the factor. The levels are machine 1, 2, 3, 4. And that's it. The whole lecture was about this output. And this is our ANOVA, analysis of variance. So the source here, remember, these are source of variability in the data. The total variation in all of those 19, DF stands for degrees of freedom. Because there are 19, let me scroll down a little bit. You see the sample sizes when you add machine 1, 2, 3, 4? Individual sample sizes 4 and 6, 10, 15 and 4, 19. There are 19 scores regardless of the machine type. So degrees of freedom here is going to be 19 minus 1, or 18. So when I see a total of 18, whatever that number is, add 1 to it and you get your total combined sample sizes. And this is your sum of squares. Now this says adjusted. Most outputs don't say adjusted. They just say sum of squares. And here you have 4 factors, right? 4. So degrees of freedom is going to be number of factors minus 1. This factor, what Minitab calls factor, that's our between sum of squares. Some outputs like SPSS, SAS, and Excel, each of them, they call these treatment. Treatment source would be treatment. Remember, treatment is factor also. So the source, this is the between in our language. This is our between sum of squares, and this is variability, not sum square, variability, source of variability between the groups. And the error is the within the groups, which we assume to be equal. So there are 4 levels of the factor. 4 minus 1 is 3. To get the 15, you subtract 3 from 18 to get the 15 here. You see how that's done? These 2 numbers should add up to the bottom number. Your sum of squares are additive also. However, this was calculated using that arcane formula. I said ignore it, don't worry about it. This is the total variability in 19 data points. And of this 0.010579 variability, sum of squares, 007076 is due to factors. The remaining of it is to the within. You see that? Now, the mean squared actually converts these into into variances. Okay, when you go sum of squared divided by degrees of freedom, you get what we call a mean squared. These are actually variances. So this is going to be the variance between, remember factor is between. And this is going to be variance within. The error is within. These are mean squares. So again, this is variance of between groups. This is variance within each group, which we assume to be common but unknown. This is an estimate of it. If you take the square root of this number, you get the standard deviation. Okay? And in fact, let me do that. I'm going to take the square root of, I got my calculator. I'm going to take the square root of 0.000234, and you get 0.000. I have 3 zeros after the decimal, and then 234. Okay. Again, actually, I want to take the square root of this number. Let me try it again. Oh, sorry, I forgot to take square roots. Very sorry about that. Let's do it again. I'm going to take the square root of this number. The square root of this number is going to be that. I guarantee you. So let me try it. I'm going to go square root 0.000234. And sure enough, I got 0.015297058. Now the reason this is off, it's like say, well, how come square root of that isn't exactly that? Is because this number 1, 2, 3, 4, 5, 6 displayed with 6 decimal accuracy. Behind the scene, Minitab keeps 16 digits behind this number. There are 16 digits, double precision. If you take the square root of those, the number with 16 digits, that's what you get. So anyway, square root of this number, which is pooled, notice, pooled standard deviation. This is what we assume to be common to all subgroups, the within. The ratio of 0.02359, remember the logic was to take the ratio of variability between to variability within, and that's what that is. 0.02359 divided by this number gives you an F statistic, 10.10. And the probability of an F greater than that, this is a probability distribution. Probability of F score greater than that is going to be 0.01. That's our p-value. Let's see how that worked. And that number is small, so we're going to reject the null hypothesis. And that's where in my note, if I go back to note, it may not look good because I've adjusted my viewing window here. But anyway, in my note, if you go back, that's what I had right below the machines. My conclusion was based on that. Okay, this portion of the output, you're looking at the means for the factor, treatment, machines, machine 1, 2, 3, 4. Sample sizes. This is cap n, but ignore it for us. Think of it as a little n, okay? The mean is the sample mean. So look how close the means are, by the way, folks. You would have, I didn't think we're going to reject this null, but I guess they're significantly different. Although, look at this. 4001, 4005. Definitely machine 4 and 2 are not different. See, their means are the same. If anything, if you look at the lowest mean and the highest mean, machine 1 and machine 3, probably these two machines are different. 1 and 3. We'll see that in a minute. These are the standard deviation within each sample. And here's a 95% confidence interval for the mean. So in other words, the population mean, estimate of population mean for machine 1 for all these jugs that are filled is somewhere between 4.046, 4.01 to 4.046 and so on. Notice 4 is in here, 4 is inside of that interval, 4 is inside of that interval, but not in this one. See, that machine 3, that's what's kind of throwing things off a little bit. That's the cause of rejection. And you can see that again here. See, 4 quarts, which makes a gallon, is not in there. Okay, let's continue on. Here comes the multiple comparison procedure. We only picked 2 key, pairwise comparisons. And there you go. Remember machine 3 up in here? We mentioned this machine 3, 4 is not inside of the confidence interval. So machine 3 is really different than the others, isn't it? These 3 machines, 1, 2, 4. Look at the means, how close they are. And there you have it. That's exactly what this is telling us. It says, okay, but notice, by the way, be careful. This isn't machine 1, 2, 3, 4, so it's not in that order. The way it's ordered is based on which means are the same, followed by the ones that are different. So that's the rule. It doesn't go by machine order, it goes by the order of which means are the same. Okay, now let's take a look at that. And internally what it does, it looks at the highest mean, next highest for those that are the same. So machine 1 average is 4.03, machine 4 4.005, machine 2 4.002. Statistically speaking, these are all the same. This is different kind of math, folks. Okay, When we say all means are the same, some of them are different, mu1 equal mu2 equal mu3 in mathematics, you say, well, that by transitivity means mu1 equal mu3, mu2 equal mu3, so mu1 and 2 are the same. That line of logic, not in statistics. In statistics, we see C4.03, 005, 4001, those are all the same. Because statistically they are not significant. They are actually the same. And it says here, by the way, means that do not share a letter are significantly different. In other words, means that do share a letter are not significantly different. They are not different. A. So that means these three means are not different. So machines 1, 2, 4 are really the same. Machine 3 is off a little. Maybe it needs some adjustment made to however the device fills, and then it'll come in sync with the others. Now, B, that means that do not share letters are significantly different. Well, this one does not share the letter. See, it's letter B. Means this machine 3 is different from the other 3. So we found the culprit for rejection. But then again, up here, we kind of had that up here too. It's pretty cool. That's the whole idea of multiple comparisons. So we did a post hoc, what we just did. Now, the graphs that go with it, very interesting. Remember with 4, when we have 4 levels of the factor and we are comparing 2 at a time, look at the comparisons here. Machine 2 minus machine 1, 3, 1, 4, 1, 3, 2, 4, 2, 4, 3, 1, 2, 3, 4, 5. There are 6 multiple comparisons. There are, again, combinatorically speaking, there are 4 choose 2 ways to pair these together, which gives us 6. And these are the 6. 2 keys, simultaneous 95. See that simultaneous? What 2 keys multiple comparison does, and this is actually now 2 key Kramer, right? Because the samples are different size. So what this is doing now, actually, it's trying to maintain the overall simultaneous, means all of them combined are kept at 95%. So we are 95% confident that collectively all of these are the means, are the difference between the means are from here to there, here to there, here to there, and so on. So this is 0. 0 means no difference in the means, right? That's why you have this red line at 0, no difference. So this one is touching the 0. So machine 2 and 1, they're no different. Machine 3, look at machine 3, you see that? 0 is not there. If 0 again is there, if the difference between the means is 0, means they're the same. It's outside of that. So machine 3 and machine 1, they're different. 4 and 1, look, it's in there. Any one of them that either it's inside or is touching here. And if you keep the mouse there, see I'm keeping it, it actually gives you the confidence interval. Look at the right 0, 0, 0, 1. You're just barely into that. 0 is just barely in there, right? And so this one is good. This one is not, but look at that. The ones that are outside, this is machine 3 and 2. See, it's outside of the 0. Machine 3, 1, outside. 3 and 1 are way off. See how far away from 0? And look at machine 3 and 4. See, those two are different. Machine 2 and 4 are very much in sync. Look at that. The estimate is 0, 0, 0, 0, 0, 3. Means they're almost the same. They're almost identical. So those two machines are right on. Okay, and continue on. Here's a box plots of machine 1, 2, 3, 4, and so on. This is interesting. And a visual of what we just found out. If the null hypothesis was true, the means were equal, we would expect to see how this line cuts down and it zigzags. It not zigzags, but it kind of dips and bounces. Okay, if all of these means were equal, wouldn't you expect this to be a flat line? Like if all of them were at 4, then this would be, the box would be down here, this one would be down here, this one up here, this one down, and you draw connected box, you expect a horizontal line, right? That's what it would be. So again, when you keep the mouse on there, I'm just move the mouse over the circle, gives you the mean. That's the mean of that box plot. And it's interesting, usually the box plot draws the median, but again, mean and median here are the same. Look at the median, second entry from above, 4.03. And for this one, sorry, I'm trying to find that mean. That's what it's, there you go. See, mean 403 and median 403. That's why these are off. See the one with the circle? Those are the means. Here's the mean, but the median is different. In a box plot, the line that you see is drawn at median. So anyway, see those means are not the same. The highest mean, lowest is machine 3. There you go, machine 1, 2, 3. See, the machine 3 is the culprit. These, machine 4 and 2, if you connect a line from 2 to 4 or 4 to 2, it's almost going to be a flat line, right? Horizontal line. So again, all of these are just confirming one another. And this is the normal probability plot. Okay, so this is actually testing the assumption, because it's normal probability plot of residuals. This is not testing for normality. This is actually testing the fourth assumption, that the deviations are the same or equal. This says, yeah, they're the same. And if I go back up here to see what were those standard deviations, they're right in here. Look at them. 013, 018, 012, 018. Statistically speaking, these are no different. That's what the standard deviations are. Okay. And let's see. I want to make sure I covered everything here. And that's pretty much it with this work. So we really hashed this thing out. We went detail interpretation of the output, and that's the whole idea. Rather than getting tangled and bogged down with the computation, we want to use Minitab so we can spend more time on interpretation. So folks, hopefully you can do this. Again, you can do 10 of these. The run of the mill is the same. So regardless of how many times you do this, as long as you have your data, another data set will look the same. You run the procedure the same way, and your outcomes would be different. But remember, out of this ANOVA, the important information is your p-value, and this number is estimate of common variance. Okay, and that's about it. We're done with this section, and that will conclude this video.